Okay, so this is a great day for Markov. This is an exciting day for me because we're doing first step analysis. And this is where I think the true power of Markov chains shows its beautiful face. So first step analysis. This is, as I've been saying, the true power of Markov chains. And this is where you go challenge your roommates to solve some probability problems, and they are going to go spinning off into horrible loops and circular arguments while you have Markov chains. So analysis. I'm going to do a running example here with a state space that is 0, 1, 2, 3. And my transition matrix, it's the same one I wrote down last time. So if you already have it, great. And there are so many kinds of questions we can answer with a quote unquote first step analysis. And I'm just going to bring up, I think, the three most common ones here. But you can certainly apply this to other types of questions. So I've got a question 1. And so the scenario here is the chain starts in state 1, or whatever you like. 1. And then I'm going to run the chain until it first hits state 3. And I want to know the expected number of steps that's going to take. So what is the expected number of steps, meaning time steps, to hit state 3? So this is what I was talking about with your friends that haven't had Markov but have had probability. They're probably going to start tracing through the matrix and think about all the ways they can hit state 3 from state 1. And you can certainly spin around in one place forever. I mean, there's just way too many things to write down. So we've got Markov chains, and to use them, we're going to need some notation. So the notation I'm going to set up here is I'm going to let T be the first hitting time on state 3, not return, hitting. So if we happen to start in state 3, the expected number of steps to first hit state 3 is going to be 0. So this is the minimum for n greater than or equal to 0, for which xn is 3. So this is going to be the stopping time, the criterion for me to stop looking at this chain. And I want to find the expected value of t given that I'm starting in state 1. And a first step analysis in Markov chain says, well, let's see where we go in the first step and then start over counting, which means that our starting position is going to be changing up. So I'm going to define a little more generally. I'm going to define ui. I like a u because it kind of looks like a mu, which looks like a mean. I guess I could use a mu as well. I'm going to define this to be the expected time until we stop the process. And we stop the process when we hit state 3. Given I'm starting at any state I. And so now in this notation, we want to find u sub 1. So let's go. U sub 1 is supposed to be the expected number of time steps until we stop, and we stop when we hit state 3. So if I start at state 1, I'm going to take at least one time step to hit state 3, which is why I have a 1 plus. And I will actually formalize this argument a little more after we do this. So starting in state 1, I have to take at least one time step forward to get to state 3. And then I look at my 1 row here, and with probability 0.5, I've gone to state 0, and now I need to start all over counting the number of steps it takes to get to state 3, starting from 0. And with another probability 0.5, my rows are really messed up. So up here I have a 0, 1, 2, and 3. So with the other probability 0.5, I will go to state 2, and then I need to start counting from there. So I want to know U1, but this involves U0 and U2, so I need to find equations for those as well. So starting from state 0, what is the expected number of time steps to hit state 3? Well, I have to take one step. And then with probability, so now I'm looking at the 0 row of the matrix, with probability 0.9, I go back to state 0 and start counting all over again. And with probability 0.1, I move to state 1, and then I have to start counting from there. So I'm multiplying things, and it's that sort of independent increments property of a Markov chain. You know, the values are not independent, but once you've gone somewhere, where you go next is independent of where you were before. So after you multiply by the probability of moving somewhere, you can, after you write down the probability of going somewhere, you can multiply by the probability of the next step. That's why I'm multiplying these numbers times these u's. And as a final one, U2, starting from state 2, how long does it take to get to state 3? So I'm going to take one step, and then with probability 0.3, so that comes from here, I'm going to figure out the number of steps starting all over again from 0. And with probability 0.7, so there's two ways I can write this. With probability 0.7, I go, so this equation is not finished. With probability 0.7, I go from state 2 to state 3 in that one step, and there's nothing more to count. So I'm going to multiply by 0, like stop counting. Or equivalently, U3, this is supposed to be the expected time to hit state 3, given we're started at state 3, and that is defined to be 0. Since we're allowing the time to be 0, we're talking about a first hitting time, not a first return time. So instead of writing this 0 up here, I could have written it as a U3, but U3 is 0. Yeah, so here's a picture. I am got state 0, 1, 2, 3. Starting from state 1, I want to know how long it's going to take me to get to state 3 on average. So I'm not at state 3 when I start at 1. So I have to take one step and I'll go somewhere. So there's my like one step that's automatically there if I don't start at state 3, and then count from there. And if that one step took me directly to state 3, that's okay because I'll count 0 more steps. So I have to take at least one step to get to state 3, unless we're starting there. Then I take 0 steps. So at this point, I usually say solve it yourself. I just want to set up one thing in case this is a problem. So we need to solve this system of equations, and we want to return U1 because that was what the question was asking, the average number of steps to get to 3 starting from 1. So the way I would do this, you do not have to do this way, is I would set this up as like a system, like a matrix with a U1, U2, U3. And then I'm going to move everything so that I have ones isolated. So in the top equation, if I take this 0.5 U0 and move it to the left, just to leave the 1 on the right, or you can do things the other way, I would get negative 0.5. And then from the U1, I get a coefficient of 1 for U1. And then from this 0.5 moving over to the left, I get a negative 0.5. So this is how I would solve it. Going across the next row, you should have a 0.1, a negative 0.1, and a 0. And that's because I have this, I have U0, and I'm going to subtract 0.9 U0, which gives me a 0.1 U0. And then I'm going to move this to the left side, giving me a negative 0.1 U1. And then finally, the last one, I have negative 0.3, and I have no U1s there, and I have a 1 U2. So this is personally what my approach would be to solve this. I have U1, U2, U3 here, and it needs to be U0, U1, U2. Thank you. Don't worry, I'm not going to drag you through this calculation every time, but I should do it at least once. So how I would solve for these is I would say U0, U1, U2 is the inverse of this matrix, and then multiply on the right by 1. Oh, I forgot my inverse, by 1, 1, 1. Okay, so do that in whatever you want to do that in, or back substitute, or start canceling things out by multiplying one equation by a multiple of another, by adding one equation to a multiple of another. But you end up with U0 is approximately 32.86. U1 is approximately 22.86, which is what we wanted to solve for, and U2 is approximately 10.86. So we wanted to know the expected number of steps to hit state 3 starting from state 1. That's how we define U1. So the answer is 22.86. Yeah, it's because of the way I defined t. So I guess I could have set this up differently, but t is the first time we hit 3, even allowing for time step 0. So if we start at 3, we don't move. We've already hit 3, so we take 0 steps. So this was a little bit conversational, but this is all I want you to do on a similar homework problem. So I have 2 more questions, but I just want to spend the time on this one to make this look a little more formal and to show you where those ones come from. So I'm going to say formally, but I mean, I think what we just did is enough, given, we're quoting the Markov property and the independent increments. But if you want to see how this happens formally, U1 is what we're trying to solve for. This is the expected time to hit state 3, given we started at state 1. I could condition on where we go at time 1. So this is the sum over all I in the state space. So from 0 to 3, the expected value of t. So I'm going to put in where I was at time 1. That's going to be I. And then x0 is 1 times the probability that x1 is I, given x0 is 1. So this is what we're doing. We're just not writing all this stuff down. And just to kind of parse these terms out, for I equals 0, 1, and 2, 3 is going to be a separate case. The expected time until we hit state 3, given that x1 is I and x0 is 1, so I is not 3 in this case. So this tells me 1 time step has passed. And so this is the same thing by the Markov property as taking 1 step and then recalibrating time to start at 0 again. So 1 plus the expected value of t given x0 equals I. So I did change from x1 to x0 because the idea is once you've taken your step, now you call this time 0 and go from there. And in the only other case, the expected value of t given x1 is, well, yeah, okay, given x1 is 3 and x0 is 1. Well, there, the path is laid out for you. You hit it in 1 time step. You started at state 1, you went to state 3, that's already given. You've reached that stopping criterion, so this is definitely 1. And finally, if I go back to the equation at the very top and start putting this stuff in, the first term is 1 plus, let me make this even more clear, or somewhat clear. This over here is 1 plus our definition of u sub I. So what I've got here is 1 plus u0, p10, and that comes from my first term when I is 0, becomes this when I is 0, becomes this when I is 0, and it gets multiplied by this probability, the probability of going from 1 to 0. And just kind of tracing that through, we get 1 plus u1, probability of going from 1 to 1, plus 1 plus u2, the probability of going from 1 to 2, plus 1 times the probability we go from 1 to 3. So that is me rewriting the equation at the very top of the screen with different notation. So this is just sort of an aside where we figured some things out, how to simplify some of these terms. But check this out. I can collect all those probabilities, like multiply them all by 1, and I get these probabilities in a sum. And then I get, I'm going to change the order, P10, U0 plus P11, U1 plus P12, U2 plus P13, U3. U3 was 0 in our problem, but this guy sums up to 1 because this is adding up everything in the first row of the matrix. And so now we have exactly what we had before. It's just that we had some specific probabilities in here and some of them were 0. But you can see we get 1 plus the probability we transition from 1 to anything else, and then multiply by the expected number of steps to get there from anywhere else. So in our problem, this is 1 plus 0.5. That was the probability of going from 1 to 0. U0 plus the probability of going from 1 to 1 was 0. U1. And from 1, we could go to 2 with probability 0.5. And from 1, we can't even go to 3. And U3 is 3. Is 0. So that'll go. And what's left is the first equation I wrote down in those 3 equations above. Okay, so I have 2 other questions, and I'm not going to go through the more formal argument there. We're just going to do it like we started here, just kind of intuitively. Take one step and then. And that's why it's called a first step analysis. Take one step, see where you are, reevaluate the situation. I've got a question, and I'm calling it question 2 in my list of kind of, I used to include this with a 4th one, which was to find the stationary distribution. I used to call these 4 questions, the 4 most important questions for Markov chains. But I think that was making them a little overrated. So now they're just 4 questions. Okay, so this question is, the chain starts in state 1 again. And I'm going to let T not be the first time we hit state 3, but be the first time we hit either states 2 or 3. And so that's like a stopping time. There's a formal definition for a random variable called a stopping time, which eventually I'll write down. But just think of it as the time you're going to stop this chain. You're going to go until, and then you're going to stop it. So we're going to stop it when we hit either 2 or 3. And I want to know, what is the probability that when the chain stops, or when we stop, we are in state 2 versus state 3. Now, those of you looking at the matrix still can probably already tell me what this answer is. In this particular problem, you'll notice, looking at the last column, that I can only go to state 3 from state 2 and from state 3 itself. So I definitely have to hit 2 before I can get to 3. So I expect this probability to be 1. But let's see how we would do it. So I am going to let, defining the T here is not that important, but it is the minimum over all n greater than or equal to 0, such that xn is 2 or xn is 3. Or you can put them in a set, and you can say the minimum time for xn to be in this stopping set. And then I'm going to let pi be the probability that the Markov chain at this random time t is in state 2, given I started in state I. And then finally, what we want to solve for is P1. Starting in state 1, what is the probability that when we stop, and we stop when either we hit state 2 or 3. So what's the probability that when that happens, we're in state 2? Again, we know it's 1, just because the only way to get to 3 is from 2. You have to go through 2. But if we pretended we didn't know that, then I would start with trying to write out what P1 is. So this is not counting time steps. So I'm not going to put a 1 plus like I did before, because that one said, how many time steps does it take? So I take 1 step and then I have to figure out how many it takes from there. This is a probability. And if in the first step I go to 2, then it's all over. But if I go to 0, we're restarting with that Markov property. We don't have to count how many trials went by. So what I'm trying to say really poorly is, with the probability we stop in state 2, starting in state 1, is going to be, I'm going to look at the 1 row, it's 0.5. And with that probability, we go to state 0. So now I have to say, okay, if I started in state 0 and I go until I hit 2 or 3, what's the probability that we're going to stop at 2 versus 3? And then looking again at the one row with probability 0.5, I have hit state 2. So just like before, I can say, okay, then with probability 1, I've done it. Or I can say, what is the probability that when this chain stops, we're in state 2, given we started in state 2? The stopping criterion is we hit state 2 or state 3, and time 0 was allowed. So this would be probability 1. So if you prefer it to look all sort of the same, I can write P2 instead of that 1 in parentheses. But again, no 1 plus. We're not counting time steps. We're just like, did it happen? No. Okay. Well, did it happen? Yes, no. Not counting time. Okay, so this has P0 in it. So I'm going to have to write an equation for P0. So P0, looking at the 0 row of the matrix with probability 0.9, I go back to state 0, and then I have to figure it out starting from there. And with probability 0.1, I go to state P1, and then I have to figure it out from there. So I have a little system of equations that you can solve any way you want, but I think I'm just going to solve it by observation, or substitute, or make a matrix and vector. But these equations imply that P0 is the same as P1, and they're both 1. So just as a quick check, plug in 1 here, then you get 0.5 plus 0.5, which equals 1 here. And these probabilities can be both 1. They're not supposed to add up to 1 because they are probabilities in a different universe. One of them is the probability in the universe where we started at state 0. And the other is the probability this happened in the universe where we started state 1. So they're not supposed to add up to 1. So we're done, and we got what we expected. Given this matrix where we can only get to 3 through 2, the probability we stop looking at this chain, no matter where we start, 0 or 1, probability we're going to stop at 2 is always 1. As a heads up, one of the questions on this homework is going to be taking you back to that bug problem with the 3 green bugs and the 1 red bug. And it's going to ask you questions like this, like what is the expected number of time steps until the red bug actually gets to eat? Or between 2 successive occurrences of, actually we don't know that yet, that's problem 3. But this bug problem on the homework is going to be like an A, B, and C, which are going to come from these questions 1, 2, and 3. Okay, so question 3, the chain starts in state 1. Okay, so notice P2 up here is 1, right? Because starting at 2, if we're going to stop when we hit either 2 or 3, then when we stop, we are in state 2 with probability 1. So P3, which didn't come into play here, is the probability that when we stop looking, we're in state 3. I'm sorry, in state 2 is how we define the P, given we started in state 3. So if we start in state 3, and our plan is to go until the first time we hit 2 or 3, we can't move this chain at all. So we will not stop in state 2 with we will stop in state 2 with probability 0. Like it's not happening that we're stopping at 3. The other way around. Starting at 3, the probability that when we stop, we're at 0. What? Words. One more time. Starting at 3, the probability that when we stop looking, we're in state 2 is 0 because we have stopped immediately.
That makes sense.
Makes sense to you. Okay, so question 3. This one's kind of fun. They're all kind of fun. Who am I kidding? So we're starting in state 1, and we're going to go to state 3 again. And I want to know the expected number of time steps in there that we spent in state 2. So the question is, what is the expected or mean number of steps the process spends in state 2 before hitting state 3? So there are 3 things going on here. Where did I start? Where am I going to stop? And what am I counting? So here is some notation you could use, but I'm not going to use it. So one idea for notation is use any letter you want. I usually use W's on these for some reason. So I can write Wij to be the probability starting at I to be the expected number of hits on state J when moving from I to K. So when starting at I and stopping at K. So in our case, we would want starting at 1 and stopping at 3, the expected number of hits on 2. So in this notation, we would want W1, 2, 3. The thing with this notation is that we're always stopping at 3 and we're always counting hits to 2. So there's really no reason to drag this 2 and 3 along. You know, every single term is going to have that 2 and 3 there. So I don't feel like writing that. I'm lazy. We're always stopping. That's me writing something. We're always stopping at 3. We're always counting state 2. There's no real reason to write that W23. There's no real reason to have that 2, 3 on the end of that subscript with 3 numbers. So we could use just a W1 because that's the only thing that's going to be changing where we start. You know, we take a step and then we're starting somewhere else. We take a step and then we're starting somewhere else. And overall, we're counting the number of hits on 2 on our way to 3, starting from a generic state I. This is a great idea, but I'm not going to do it for reasons. And that reason will maybe be hopefully apparent after this example. The point is you can define it however you want, and this is what I'm going to use. So we'll use this notation. And if you want to use your own notation on the homework, as long as you give me some kind of legend and say, I'm going to let Vik be the probability that, then it's okay. So this notation, meaning I'm going to say Wij, this is the number of hits on J started from I and stopping at 3. And hopefully I will convince you that this was not a useless dragging around of the subscript 2, because J is going to be 2 throughout this problem. Okay, so we want, in my notation that I have settled on, W1, 2. I don't want the number of hits. I want the mean or expected number of hits. Okay, so let's go for it. Starting at state 1, what is the expected number of hits on 2 on our journey to 3? So we're back to time steps. Remember, question 1 was time steps and question 2 was probability. And in question 1, when we had time steps, we always started with a 1 plus. But I'm not going to do that here because we're not counting all time steps. We're only counting hits on state 2. So although I can't do it in this particular matrix, if I could go directly from 1 to 3, then I had never hit state 2. So I should not do a 1 plus until I know that I've hit state 2. So I get, with probability 0.5, I move from 1 to 0. And now I want to say, starting from 0, what is the number of hits on state 2 before I hit state 3? And then with the other probability, 0.5, I'm at state 2. So I want to say, starting from state 2, what is the number of hits on state 2 before I hit state 3? And you might be thinking, well, I've already hit state 2. we'll take care of that when we write down the equation for W22. But I'm going to need a W02 to solve this. So starting from state 0, I won't necessarily hit state 2. Yes, in this particular matrix where I can only get to 3 through 2, yes, it's true. But in general, I would just look at the probabilities in the 0 row, and with probability 0.9, I will have moved to state 0 or stayed at state 0. So I want to start again, counting the number of hits on state 2 starting from state 0 before we stop at state 3. And then with probability 0.1, I have moved from 0 to 1, and now I want to start at 1, counting the number of hits on 2 before I hit state 3. You can see what I meant about dragging that 2 along. There's a 2 on every one of them. But I have a reason for this. So the other one that's unknown here is W22. So I'm starting the chain at 0, 1, 2, state 2, and I want to go until I first hit state 3, and I want to count the number of hits on state 2, and there's already 1. So I have a hit on state 2. And if you choose to use my notation, this Wij, then you're always going to get that 1 plus every time you have like a Wii. You're counting the hits on I, starting from I. And then looking at the 2 row with probability 0.3, I'm going to start over from 0, counting the number of hits on state 1. No, state 2, sorry. Counting those. So with probability 0.3, I went to 0, and now starting from 0, going until 3, how many times did I hit 2? That's what I want to count. And then with probability 0.7, I moved to state 3, and this is we count nothing more. So to make it consistent with what I've written in the past, I'm going to put a 0 there, but then also say that starting from state 3, if I'm going to stop the first time we hit state 3 and try to count the number of 2s, we stop instantly. And so this is 0. We never get to travel or see any 2s. Again, there's a 2 on every single subscript, so you don't have to write it, but I have a follow-up example where this is going to be useful. So solve this system. I did it with a matrix and inverted it, multiplied it by a vector, and I got W02 was, actually I got them all to be 1.43 in rounding. It's just a particular kind of matrix we have where we're forced to go in a certain route to get to 3. These are all 1.43. This one seems bizarre at the end because starting from state 2, you're already counting a hit on state 2. So I feel like this should be more, but it's not. And that's because you have a high probability of moving directly to state 3 and not counting another one. So it's a little unintuitive, at least to me, why this third one should be the same as the others, but we were starting from state 1, so this is what we wanted, and that is the answer. Starting from state 1, going until state 3, we're going to hit state 2 an average of 1.43 times. Okay, so as a final thing here, I want to kind of motivate why I use that second subscript. So note, if we compute some others, which is going to involve different systems of equations, namely, I went and computed we just computed W1, 2, 3. If we go back to the full notation, so W123 was 1.43. I don't need the 3 there, sorry. Let me stick with the 2 subscripts. Okay, but writing a separate system of equations I computed W10. So this represents starting at state 1, stopping at state 3. What is the mean number of times I hit state 0? That's a whole different system of equations. And I got 18.57. And then finally, I computed starting at state 1 and going until I hit state 3, what is the expected number of visits to state 1? And I got 2.86. So these were from entirely different systems of equations because I was counting hits not on 2 and on something else. But check this out. W10 plus W11 plus W22 here, if you add them up, you're going to get 22.86. And that, my friends, is what we saw in question 1. This is saying, if I start at state 1, how long does it take me to get to state 3? That's what U1 was. And this is saying what happens along the way. Well, I spend this many steps in state 0, and I spend this many in state 1, and this many in state 2 along the way, and they add up to the total number of steps it takes to get from 1 to 3, which is awesomely satisfying. And so that's the reason I use the second subscript, because I did want to change up the second subscript for this example. Wow. So as a final thing for today, I wanted to begin a discussion that's going to extend into the next class, obviously, about mean pattern times. So this is where you've got a monkey with a typewriter hitting keys, and you want to know how many keys they're going to hit until they spell Markov. On average, how long is it going to take? This problem is hard if the thing you're looking for, the words, have some overlap to them. Like if you can start spelling Markov with the end of Markov, then this is a lot harder. Like if you're looking for the word Markov in a whole series of letters, if we were actually looking for the word my, then the end of the word is actually the beginning of potentially a new word. And so the case we're going to talk about here is when we have non-overlapping patterns. To do the overlapping patterns, you can do it several ways, but I think the easiest way to do it is using a martingale, which is a cool tool of probability. If we have extra time at the end, I'll try to fit martingales in this course, but I highly doubt it. But yeah, so we want something non-overlapping, like a word like Markov. And I have a kind of brute force way to find this. And it's funny that I know I'm out of time. It's funny that I call this brute force our first step analysis. I can redefine things and use the first step analysis. And that's not brute force like your probability roommate is doing, but it is compared to another technique I have for finding the mean pattern times. It is so slick, it will blow your mind. Thank you.